We are presenting about one of the sequences which is very common in downstream processing events. When you are having a fermentation broth, the first few steps are like harvesting the culture broth. So concentration of the product can be very low, like 0.1 to 5 gram per liter. And product concentration is definitely much lower, 0.1 to 1%. But subsequently, we have a couple of steps like cell removals. At the first steps, we will say, which can be done by filtration, where concentration is around 1 to 5 gram per liter. And product quality is 0.2 to 2%, still much lower. In many times, after cell removal, we can have extracellular or intracellular products. Depending on if it is intracellular products, we can have to disrupt the cell, break down, and then the intracellular products should be recovered. And in this process, when you are talking about recovery, extraction is one of the important steps where concentration can improve significantly. So from 1 to 5 gram to 5 to 50 gram per liter, so around 10-fold increase. It is very important steps because in these steps, the large volume of aqueous phase we can avoid. Though extraction is one of the method, we can also have adsorption process. Subsequently, you can have product enhancement to purify it, which can be chromatography or crystallization process. Crystallization is also referred as a polishing process in this workflow. Now, extraction theory, basically when you are using two immiscible solvent, our target compound is there in aqueous phase, but the compound is preferentially soluble into another solvents. So solute to move from original liquid like a culture broth to your immiscible organic phase. So basically you're using two different solvent and our target compound is getting partition between the two phases. And after some time, they will reach one equilibrium. Equilibrium is essentially a scenario where there is no more changes in concentration between the two layers. So essentially, you can assume they have reached an equilibrium stage, concentration remain constant. Now, if we say like this way, there is one important aspect that is called concentration ratio between aqueous phase and organic phase, these two layers. So organic to aqueous ratio is called partition coefficients. A higher partition coefficient is desirable because we can have large amount of target compound moving into the latter phase or organic phase. In small volume organic phase. So essentially volume reduction is there. It is making the compound concentrated. It is more easy to process also in that scenario. In many times K is constant, though the partition coefficient, what you are referring as concentration ratio, can be non-linear, but for easier understanding or many of the cases, it remains constant. But still, it depends on what kind of solute, what kind of solvent. Depending on these three, the partition coefficient can be different. What is the basic purpose and what is the process involved here? So, aqueous phase contains large amount of our target compound where we are adding some organic phase at the top. Then we are mixing. Mixing actually enhances the interfacial area between the two liquid. So your target compound can move into your organic phase, and then you are allowing the mixture to settle down. So phase separation is happening. And once phase separation is done, the organic layer can be utilized as per our requirement. We can concentrate it further. We can remove the solvent. This process can also be done in industrial process like centrifugal extraction process, where mixing and separation can go side by side. So in a single steps, we can recover. So this process is possible to concentrate the compounds of interest and separate them from undesirable compound in a single step manner. Why do we do the extraction process? There could be many reasons for this case. The partition coefficient is very high, so we know the compound moves preferentially to the organic phase. So our compound can be transferred into liquid phase in a small volume. So things are concentrated, easy to handle, easy to maintain. Like here, one example, I'm having 1000 liter of aqueous phase containing 5 gram of target compound. Assume I'm mixing with 1 liter of organic phase, water immiscible phase. And after mixing, if I find much of the compound of the 5 gram has moved into our organic layer, So this movement is essentially causing us to have a concentrated organic layer around 4.8 gram. So much of the compound has moved, but the volume you can see from 1000 liter, it is becoming just 1 liter, so small volume. The extracting solvent could be more easy to evaporate because many of the times non-aqueous phase liquids, organic water immiscible solvents, they are volatile. So it is easy that we can, with less amount of energy, we can recover the solvent back, we can reuse again, and our target compound is separated. Other impurities in the organic phase, which is aqueous phase, which is already present there, that can also be separated because their partitioning coefficient for the impurity may be totally different. Let's see one example here. Assume I am having 1000 liters, 10,000 liters, 5 gram of target compound, 5 gram of impurity. And I'm mixing with 1 liter of organic phase. At the end, I'm finding that 4.8 gram of our target compound has moved into organic phase, but just 0.3 gram of the impurity has gone up. So essentially in aqueous phase, which was 50-50, their concentration was there. I mean to say 1:1 ratio. But at the end, when separation is done, our target compound is 4.8 gram, but impurity is just 0.3 gram. So our purity has significantly improved in compared to our aqueous phase process. In case of industrial centrifugation, we can use a set of centrifugation extracting units connected, and the aqueous phase, which we are referring as heavier phase, and the organic phase, which is lighter phase, they can come into contacts through the centrifugal extraction units, and they are moving in opposite direction. So we can have counter current extraction process, which is good capacity. For example, here 150,000 liter per hour we can have a capacity. It is used in industrial process, and if it is efficient in separation, we can see the flow. So we can have extraction inlet, for example, in the bottom left side to right side. On the other hand, we can also have the extracting agents outlet after extraction process is coming from right to left side. So this is a counter current extraction units. Each unit is, so here actually the liquid mixing and separation process takes place. Many times this process can also be integrated into fermentation process altogether. For example, in this case, we are talking about the fermentation units. Some of these, after the settlement of the cell, the culture broths containing our target compound can be siphoned into one extracting units. And these target compounds are now separated preferentially into a separate solvent layer. And the aqueous phase, the remaining molecule or nutrients, they can also be recycled back into a fermentation unit. So essentially, separation happens in a connected extraction unit. This process can be go online in this process. So fermentation and extraction going side by side. And it is possible to have a pilot scale, industrial scale as well. This is really one innovative approach for separation where upstream and downstream comes close to one another. Few questions are there. Can you use extraction for any products? Essentially not. The products must be separated or must be partitioned into organic phase, then only you can use. Products should be stable also in the participating organic layer. Can you choose a solvent based on your products? There is a reason, there is some approaches on this because our solvent should be water immersible. A solvent should not make any stable emulsion formation. Many times solvent are immersible, but mixing cause them to emulsify. So separation is really impossible in that cases or difficult. Can we modify? Yeah, the extraction process can be modified because many times our target compound is weak acids. So they can actually ionize. The partition coefficient is basically talking about partitioning of the unionized fractions between aqueous and organic phases. So if I increase the proportion of unionized fraction in the aqueous phase, partitioning into organic phase will be improved. And that can be done by changing the pH in aqueous phase environment. So changing pH can basically control the degree of dissociation of your compound. If I can minimize the dissociation or unsaturated product, if I can keep it high, partitioning into organic phase can be improved. Is just high extraction efficiency sufficient? No, it is not, because in case of biological molecules where activity is important, stability is also really important. So these criteria should definitely be considered. After extraction, how we are going to recover process? Is it amenable or is it going to be challenging for stability of the products? That should also be considered. Here we can also use different kind of solvents to select or screening process. This list we have taken from Sigma, which is talking about different pair of solvents which are miscible or immiscible. So essentially, when you're talking about from aqueous phase or water, so here this basically this row is talking about which are miscible or immiscible with water. So the cells without any dots are essentially miscible one. The other way, the blue dots are immiscible. So we have a good number of solvents. Possibly we can try like here, ethyl acetate, heptane, hexane. These are one of the important solvent, MEK, methyl ethyl ketone. So other different solvent can be utilized. So this list can be useful when you are talking or when you are thinking about inducting one extraction, liquid-liquid extraction process.